This is the first video for Chapter 6. In Chapter 6, what we're going to do is we're going to take everything that we learned about sampling distributions and apply them to specific tests that we can run for inference for statistics. This chapter specifically is focused just on proportions. So remember in Chapter 5, we talked about population parameters, and these parameters of interest were proportions or means, right? We were either counting the percentage makeup of a sample, or we were talking about an average value of a sample. And while we will still think of both of those two measurements, this chapter specifically focuses on proportions. We will come back to sample means, we will come back to averages in the next chapter, Chapter 7. However, the foundations of concepts that we're going to learn for both chapters will obviously take place in this chapter. So Chapter 6 will have a lot of information. You'll learn the basics of a confidence interval and a significance test. After that, we're going to learn how to apply it just to population proportions. Next chapter, we will cover population averages. The first inference method that we're going to learn are confidence intervals. So let's begin. When we have a population and want to find a parameter for this population, it's often impossible or too expensive to actually perform the census that we need to find the true population parameter. So we look at a sample. In this unit, we're going to see how we can take a small sample statistic and infer the parameter for the entire population. If you remember, for the King's Page, our school's newspaper, in the fall, they made a claim to talk about the proportion of the student body whose favorite candy was candy corn. What we could do as statisticians is we could actually check their claim and see how confident we are that their claim is true. And later on, we'll learn how to perform a significance test to either accept or fail to accept that claim. So just a couple of vocab terms that are going to be really important for us. The first is a point estimator. A point estimator is a statistic that provides an estimate of a population parameter. The value of the statistic from a sample is called the point estimate, right? So think about this entire method that we're doing. We are going to try to guess, we're going to make an educated guess at the true population parameter based off of a statistic that we collect from a sample. So that sample that we collect, say we collect a sample of 20 students. The statistic that we collect from those 20 students becomes our point estimator. It's the basis of everything that we're going to do. This is the first piece of information we collect, the point estimator. So here's just an example to help guide our thinking. Assume that I took a random sample of 16 observations from a normal population with a mean M and a standard deviation of 20. I then calculated the mean X bar. Really quickly, instead of M, the mean should be mu and the standard deviation of 20, right? Since we're talking about a population and we're talking about averages, remember the sampling distribution of an average will mimic that of the true population. So it's really important for us to know that the distribution is normal. We're then going to calculate X bar. So I randomly grab 16 people and I take the average of whatever I'm measuring, right? X bar for my sample is 240.8. This is my point estimator. I took a sample, I calculated the statistic here being the average. So here's my question. How close is this point estimator, the statistic that I just collected, to the actual mean, the actual average for the entire population, right? So let's think, how would this point estimator vary if I repeated this process and took many samples, right? We talked about a sampling distribution, right? We were able to describe our sampling distribution. That's everything we did last chapter. And we were able to describe the sampling distribution based off of the shape, the center, the spread, and potentially any outliers. Remember, we want to use SOX. Right, so here we've got two. We've got the population's distribution over here on the left, right? We've got the true population parameter, we've got the true mean of the population, and we've got the standard deviation of the population. Through that entire population, I can take sample sizes of 16. Remember, we want all the sample sizes to be the same. And each sample that I collect is going to give me a different average due to sampling variability. All right, here's 3 different examples. But based off of taking one of those samples, I can create a sampling distribution. Right, here's a sampling distribution on the right. Technically, this is for X bar. Remember, the true center of this sampling distribution is the true population parameter, which to us right now is unknown. The standard deviation here, remember, is based off of what we calculate. For us, technically, in this example, if the population standard deviation is 20, remember, we're dealing with sample means, I know that the sampling distribution's standard deviation is sigma over the square root of n, which here for us is 20 divided by the square root of 16, right, giving us 5. So for my sampling distribution, I can say it has a standard deviation of 5 in this example below. So let's take a moment to think of the empirical rule. We learned the empirical rule at the very beginning of class that within 1 standard deviation on either side of the center, there's 68% of the observations. With 2, there's 95, and within 3 standard deviations on either side of our center, we've got 99.7. So in a normal distribution, 95% of the data lies within 2 standard deviations from our center. That's really important for us in this example. In our example, we have a sampling standard deviation of 5, right? The sampling standard deviation of 5. I'm gonna go ahead and make a note of that. So we have a 95% chance of getting a sample mean that lies within 2 standard deviations on either side, right? 2 standard deviations on either side is 10 units. 10 to the left of the center, 10 to the right of the center. So let's rethink our claim. Right, in this example, we said 10 on the left, 10 on the right. Right here, if we're talking about the sampling distribution of X, and we're saying that we are centered at 240.8 based off of what we collected, right, based off of the sample that we collected, right, our point estimate, we know that we are 10 units to the left and 10 units to the right of that, we're going to get 95% of our data. So subtracting 10, we're at 230.8. Adding 10, we're at 250.8. Right, so we've got a 95% chance. We can say that we're 95% confident on either side of this point estimate, the true population parameter will lie. And I'll restate that a couple of different ways in this video. But take a moment to let that sink in. We've got our point estimate. This is what we collected. And we know that we are adding 2 standard deviations. And over here, we're subtracting 2 standard deviations. So let's talk about what a confidence interval is and what the margin of error is. That's just all conceptual. Now we'll learn the actual formulas for that. A C% confidence interval gives an interval of plausible values from a parameter. The interval is calculated from the data and has the form point estimate plus or minus the margin of error. This is going to be a formula that's going to help us through the rest of the entire course. The point estimate, right, what we've collected, plus or minus some margin of error, what we're allowed to be right and wrong. How far off can we be to have a specific confidence interval, specific confidence level? And you'll see right now, the difference between the point estimate and the true parameter value will be less than the margin of error in C% of all samples. So let's talk about a confidence level. What is a confidence level? The confidence level C gives the overall success rate of the method for calculating the confidence interval. That is, in C% of all possible samples, the method would yield an interval that captures the true parameter value. So if I were to repeat this process, if I were to take a sample and create a confidence interval, start over, collect another sample, create a confidence interval, start over, collect another sample, and create a confidence interval, the confidence level will tell me the percentage of confidence intervals that actually has the true population parameter. So let's talk about interpreting confidence intervals and confidence levels. To interpret a C% confidence interval for an unknown parameter, this is what we say. We are C% confident that the interval from the lower bound to the upper bound captures the and whatever parameter we're truly talking about. So if we were to go back to our example, talking about a 95% confidence level, we could say we are 95% confident that the interval of 230.8 to 250.8 captures the true population mean. We're 95% confident that the interval of 230.8 to 250.8 captures the true population mean. This is how we would interpret that. So let's take a second to look at this example. 2 weeks before a presidential election, a polling organization asked a random sample of registered voters the following question. If the presidential election were held today, would you vote for candidate A or candidate B? Based on this poll, the 95% confidence interval for the population proportion who favored candidate A is 48% to 54%. Remember, this is a proportion. We're talking about percentages here. So the confidence interval is 48% to 50%. So let's interpret this confidence interval. What could we say for this confidence interval? Well, we know it's a 95% confidence interval, so we can say we are 95% confident that the interval from 48% to 54% captures the true proportion of all registered voters who favor candidate A. That's how we would interpret that confidence interval. B says, what is the point estimate that was used to create the interval? What is the margin of error? Now remember, the point estimate is always in the center of our interval. So how could we figure out what the margin of error is? How could we figure out what the point estimate is? Well, remember, the point estimate is dead in the center, so we can say the point estimate is 51%. the margin of error is 3%. If I needed to write that out in a formula, I could say, remember my point estimate plus or minus my margin of error. Right, if I were to follow that out, 51% plus 3% gets me to 54. 51% minus 3% gives me to 48%. So the margin of error is 3%. And the point estimate is 51. Point estimate, estimator. C says, based on this poll, a politician reporter claims that the majority of registered voter favor candidate A. Use the confidence interval to evaluate this claim. Well, remember, this is all based off of a sample that we collect. The one sample that we collected here doesn't tell us the sample size, but the one sample that we collected here, we need to remember, had a 51% of people who favored candidate A. And we have a margin of error here, right? The margin of error is going to take into account the sampling variability that we've talked about. But technically in our interval, we do have values that are less than 50%, right? Although there are more values that are greater than 50%, although the actual proportion for the sample we collected was greater than 50%, we have to recognize that there are values less than 50%, which does not show that the majority favor candidate A. So we're going to answer this by saying, because there are values less than 50% in our interval, we cannot support the claim. So remember, every time we take a sample, we're going to get a different statistic. That's because of sampling variability, right? Even looking at this example here, going back to the one that we talked about with sample size of 16, all three of these samples technically gave us a different point estimate, right? Our margin of error, right, the plus or minus 10 on either side was based off of the first one that we collected. However, we've got a lot of different confidence intervals, right? At this point in statistics, we need to repeat this process over and over to help make sure what we are saying is true. So because of that, let's go down here really quick. Because of that, we can talk about all of these different confidence intervals that we're creating, right? In this diagram, here is the true sampling distribution of X bar, all right? This is what we did on our first one. The true population parameter is the center. Remember, that's true for all sampling distributions. However, all of these red dots represent the statistics that we're collecting. All of these red dots represent the sample statistic that we collected for that one sample. And we created a confidence interval for each one. That is what the green line represents. This is our 95% confidence interval. Well, if you've noticed, based off of the confidence interval that we created at the very beginning, this one, this interval right here, this blue interval misses the true population parameter, right? Our true population parameter is right here. The blue one does not include that value whatsoever. This one doesn't help us, but the rest do. The rest of them do actually capture the true population proportion that we're looking for. In this case, or not proportion, mean, in this case, the average, right? So that's what our confidence level means, right? If I were to repeat this process, let's say for 100 times, if I have a confidence level of 95%, that means 95% of the intervals that I make, of samples that I collect, will capture the true population parameter. 5% will not. So because we take many, there is a chance that our population parameter is not in our confidence interval. To say that we are 95% confident is shorthand for what I said earlier. If we take many samples of the same sample size from this population, about 95% of them will result in an interval that captures the actual parameter value. Now you can change your confidence level, right? You can make a 50% confidence interval level, a 50% confident interval, right? Which means if you were to do this 100 times, only 50 of those confidence intervals will actually capture the true population parameter that we're looking for. So how do we make them? Well, the wider the interval we have, the greater confidence, right? Think of this really long confidence interval. Well, you're probably going to capture the true population parameter. But just because we've got a very wide confidence interval doesn't necessarily help us. We do want a smaller interval, but we still want to maintain our high percentage of confidence levels. So we need to think of our standard deviation, right? The bigger the sample size we have, we're going to get a smaller standard deviation. If you remember our formulas, the standard deviation for proportions was the square root of, just going to write the formula out. And if we're talking about the standard deviation for sample means, we had this formula. Both of them are being divided by some form of the sample size, right? The square root of the sample size. So the bigger the sample size, the smaller our standard deviation will be, which will construct a less wide interval. So if we really want to keep our confidence level high, but we want to make a smaller window, we need to increase that sample size. The bigger the sample size, the less wide of an interval we can have to maintain our confidence. So let's go back to our example way earlier before. In our confidence interval with a sample mean of 240.8, we wanted a 95% confidence interval. This required two standard deviations on either side. So we have the equation 240.8, our point estimator, plus our margin of error. Remember, our margin of error was 10. Our margin of error was this part after the plus or minus sign. So to break down the margin of error, right? The margin of error can be broken down further. The 2 is known as the critical value. This is a multiplier that makes the interval wide enough to have the stated capture rate. You can think of this critical value as how many standard deviations, right? 2 standard deviations, so on and so forth. The critical value depends on both the confidence level and the sampling distribution of the statistic. So the margin of error has the critical value. This right here, the 5, is the standard deviation of the statistic. And I'll actually cover that in a different video. The standard deviation of the statistic. So the margin of error is the critical value times the standard deviation of the statistic. Never mind, we'll cover it right now. The confidence interval for estimating a population parameter has the form statistic, the point estimator, plus the critical value times the standard deviation of the statistic. The statistic we use is what we collect from our sample. right? The second term, all of this together, like we talked about before, is the margin of error. So this is the idea of a confidence interval in a nutshell, right? The the idea of this confidence interval will apply both to proportions and means. We're going to do both of those separate. This unit, we're going to focus on proportions. We'll cover means in chapter 7. However, this idea of confidence interval applies to both.